Hi everyone. Please don't forget to subscribe, like, and share my channel. That will help me to create more such videos. So, in my last few videos, we've been focusing about fuzzing. We have seen how do we fuzz our damn vulnerable C program using WinAFL or AFL or HawkFuzz or other various fuzzers. We have also seen how do we do binary diffing using IDA and predict plugin. So in this video, I'm going to talk about a uh, topic which is very interesting, and that is how do we do time travel debugging using WinDBG. So WinDBG has a preview version which offers this capability where you can actually go back and you can execute your code in the reverse order. Generally, when you run a program, you always move forward. You cannot go back. But WinDBG preview offers this feature where you can go back. You can go to the previous uh, code line which has been executed. You can undo that. You can go back again, and that will actually change all the register values and everything. So you can easily figure out the root cause or any vulnerabilities and issue which you can analyze. So in this video, what we are going to do first is that we will see our damn vulnerable C program. You can go to this site, that is github.com target05 damn vulnerable C program. And if you are following my videos, you will notice that I have released one harness for Windows DLL, and I have converted our program to a Windows DLL which contains a lot of vulnerabilities. So you can download it from here, that is inside Windows DLL folder. And if you want to fuzz it using WinAFL, you can download harness from here as well. So you can see it's a very simple C program which simply calls our time vulnerable DLL, calls the process image function for that, and you can actually compile that. So when you fuzz this program using WinAFL, you will get a lot of crashes. If you are not comfortable with this program, I will quickly walk you through the source code. So this is the source code for NAM vulnerable C program, that is imgv.c. And if you will notice, you can see that it has one main function over here, which calls process image function. And inside process image function, it expects file name as a parameter. So it will open the file name and then it will read the data in this structure, that is header. This is a imaginary header format which I have specifically designed for this videos. And you will notice that it has a character which is on 4 bytes, character header which is on 4 bytes. There is an integer weight, there is integer height, and there is data of 10 bytes. So you will see inside process image function that inside a while loop, it will read this data from the file, from the provided input file, and then basically it will try to do a lot of operations on image width and image height. So basically these two are the integer variable where it will do a lot of operations, like it will add them, it will subtract them, it will divide them. So that will cause a lot of vulnerabilities like integer overflow or integer underflow, deep buffer overflow, use after fill double free, etc. So I have already first this program in my last initial video. You can go to my channel, you can check it out. And what we will do here now is that we will use WinDBG's time travel feature, and we will see how do we use that. So I'm not going to talk about all the commands for WinDBG. I am basically going to show my approach, which I use when I'm analyzing any particular vulnerabilities. And I generally don't use many commands. So first thing you need to do is that you need to install WinDBG. You can go to Windows Store, you can search for WinDBG Preview, and you can download and install from there. Now, once you install WinDBG Preview, you need to run it in the administrator mode. Otherwise, you cannot use time travel debugging feature. Basically, there are different steps when you want to use time travel debugging. First thing is that you have to run it in the administrator mode. Uh, let's simply run that. I will show you. And if you go to the file, you will see it has a lot. And here you can specify your executable file inside executable function and arguments, whatever argument it takes. In my case, I have selected damn vulnerable project, which calls damn vulnerable DLL, and as an argument, I am giving one file that is one.img. This over here. This causes a crash inside our damn vulnerable DLL, and there's a start directory. And now, if you want to generate the trace, you need to select this checkbox that is record with time travel debugging, and then you need to click on configure and record. And you can select a location. In my case, I have selected time vulnerable project release, and let's click on the record. So what it will do is that it will execute this program and it will generate one trace file. We need to wait for 2 seconds. So it actually executes the program first. We will notice the output over here, and then it will start the program. You will see a lot of messages, something like that, created index, series, and all these things. And on the bottom side, you will see there is one exception, or there is one error kind of thing in the rack, which shows that exception has occurred over here. You can see there is a program counter over here. So this is the address where it might have caused a crash. So we will simply do G over here. We will type G and we will let it run. So you'll notice that when I type G, which means root, it will execute our program. There is no breakpoint, so it will start executing that and it will crash. So you will see that we are getting one access violation code over here, and it's crashing while moving some data from one register to the ESI register over here. And that's it. So we can actually change call stack. So let's type AB over here, and you will notice that this is a call stack. So our program is crashing inside the process image function inside this location, which is over here. So that's it. And what we can do now is that we can simply stop the debugging, and now onwards we don't need to run this program. We don't need this input file. It has already generated one trace file. I will just show you. So if you see on the screen, there is a file that is a damn vulnerable project 02.run, and you see the timestamp, that is the recent one, 10:59 over here. So this is the trace file which we can now use in our WinDBG preview, and you can simply double click on that. That will open WinDBG preview. Something like this you can see, or you can actually go to file and you can click on open trace file and you can select this run file. So it is actually a trace file which contains execution information for WinDBG. And as I have shown in previously, you will see there is the crash which occurred over here, there's a mark over here. So if you click on that, you will directly go to that location that was causing the crash. And there are certain WinDBG commands like PX, you can actually trace out, but these are not actually needed. You can simply click on the links over here. Like, so there are different indexes, so you can just click on that and you will jump to that particular location. So in our case, let's run it again. We'll simply type G. Remember that we are not debugging this program live. We are simply replaying one trace file which has been collected for WinDBG preview. So we just run it. It says I know the trace. We will restart it. We can simply go back. So you can go back by typing G minus, that means execute on the backward. So you will notice that now we are in the start of the program, that is anti-DLL LDR initialize, and this is the start of the program. And now when I just type G, you will notice that we are crashing over here. So if we want to go back step by step, we can use a command that is p minus. If you type p minus, what it will do is that it will execute each instruction one by one from the backward direction. So right now it is executing this instruction. If I type p minus, it will move up, move back one instruction. So you will notice over here, just one section, you will notice this will move back by one section. And similarly, if I type p minus, it will move back. So the first command was G and G minus, that is just for forward and backward execution. Then P and P minus, if you type P, it will simply move forward one section, or if you type P minus, it will move back one section. And suppose if you want to come out of this function now, say here it is right now, it is inside process image function. We just want to come out. We type G minus U. So what it will do is that it will come out of that function. You will see it over here, the source code for this. So it is at the process image. It is calling the process image function now let's do a step in. Or before that, let us see. Uh, yeah, okay, I think it should be fine. If you look over here, there is some parameter being passed. So let's do p minus, and there is a printf over here, which actually simply prints the hello message over here. So let's move on. And now we will do step in. So you can simply click on the step in. You can even place F11 effect. So let's go inside, and now we are inside the process image function. So if you remember, our program was crashing over here. We will simply do step over one by one. So let's just write P and click press enter. We'll see that it's simply going forward, executing each instruction one by one. And we'll notice that there is one call over here. So we will simply pass that, because there may be a lot of file open calls. Now here you will see that it's calling another function. So we will pass that as well. And let's try to pass this. At the timeline, you will see that there is we are very close to the location where our program is crashing. So we'll go step by step. We'll simply do P. We are almost there. So let's do step in over here. You will notice we are close to the location where we are crashing. So we'll simply do a step in. You will notice that it is actually a malloc call. So let's do a step out. We'll type P minus. We move back, and we will see the parameter which has been passed. So EBX has been pushed over here. We will go to let's see what is there. There is nothing over here. So let's go. We will step over this, and we will see that EX is 0. It means that there is no memory which has been allocated. And next we will see that the program is trying to copy some data to ESI location. Sorry, it is trying to copy some data. Let's go. You can simply type T over here, and next we will see the data is being copied to ESI. And there is again no section. So ESI is actually the source over here, and you will notice that there is some register over here, and if we see the value, it is not. So ESI is not a valid memory location, and therefore you cannot write it. So if you go back to our damn vulnerable C program, you can see it over here that there is a variable that is size1, which it has been calculated by adding image width and image height, and then this value is being passed to malloc. Now in our case, malloc was either very large value over here, which was EBX, which value. This was the malloc one, and you can see EBX, it is this value. So this is actually a very large value, and chances are that the malloc will fail over here. So memory will not be allocated, and therefore we are seeing EX as 0. So if you relate to this, this is actually a integer overflow condition over here, and we are not verifying if malloc is successful or not. I think we should have checked over here that if buffer1 is null, if then it's so, then we should have skipped this thing. Program should have returned, or it might avoided this copy over here. But since we are not doing here, buffer1 is null, and we are trying to copy image.data, which is of 10 bytes, if you notice over here, to an unallocated memory. So that is actually causing a crash over here, and this is what is happening over here. So this was the root cause of this, and you can actually trace this out. For example, if you see, if you go back one more time, you will see that this location, that is ESP plus circuit, it contains 414141. Now, if you want to see which instruction has returned this value over here, what you can do is that you can simply put a breakpoint, that is break on axis, right 4, W4, and this location. And now you can simply type G minus. It means that execute our program in the reverse order. We'll go back and we can figure out that which instruction at which particular location our program has returned to this particular location. So you will notice that this location contains 414141, that is A, and let's simply do P minus, and you will notice that the value has been changed. So this is the location. There is a move instruction. If you see, it writes EDX. If you see the value of EDX now, it is 414141, and it writes EDX to this memory location, which is bounded by EDA. You see EDA, it contains this location. So this is first state. When type P, you see the location has been written by 414141, and so we found that EDX contains 414141, which is taken from our input file. Now next thing we need to do is that we need to trace out how does EDX catch this 4141 value. So we can simply do P minus, or if it's a large program, you can do G minus over here, and you can basically do G minus, so you will come out of that function. You will multiply the value of EDX. So you will see that it will change the current function is changed over. As of then you just need to execute till the time. We'll figure it out. So let's do P minus, and we will see. We have to monitor the value of EDX. So we'll notice that it is 4141 right now. Let's again do P minus. Let's do that. So okay, it has been changed. Okay, it has been changed over here. You will notice that it has taken the value over here. So this is the location. Now this value is coming from the location from the ESI. Remember ESI, right? ESI contains, we'll see over here, ESI contains some memory location which actually contains this. So let's go to this location, which is spotted by ESI, and you will see that this location actually contains AAA couple of times over here. And if you go up, you will see, right? This is actually the input file which we have given. So in this case, if you just go to this location, you will notice that it contains this file, which starts from this location 3D, and it actually starts after hello. So let's open our input file and see our WinDBG. You will notice the same thing over here, which actually contains our input file, and this is actually the in-memory copy of our input file. So this is how you trace a particular field inside your input file, inside the POC file. This was a very small example, but this approach should work whenever you are fuzzing any real-life Windows program as well. So I wanted to keep that simple so that people can understand. I use very selective commands like G or P, P minus, etc. But there are a lot of commands in WinDBG. You can even click on this particular link or something like that, and you will go to that location. Let's say I want to go back to this location. I will simply click on here. So you will notice that execution starts from that location. So this is how you use time travel debugging using WinDBG to identify root cause of a program. Uh, uh, how do you this is how you identify what field, what value inside the file was causing the crash. And I hope that you have enjoyed this video. And if you enjoyed this video, feel free to like, subscribe, and share my channel. That will help me to create more such videos. If you have any questions, feel free to post it inside the comment section of YouTube video. I will be sharing this compiled binary in GitHub before. I will put the link in the video's description so that you can try it out yourself. I will also be sharing this POC file. And till next video, stay safe, goodbye, and enjoy. Bye.